This lesson deals with the step response of an RL circuit. You can find these notes in the course ebook in Chapter 5, starting on page 22. Suppose that we have a linear circuit that has a switch in it that changes state at some time t equals t0, goes from an open to a short or a short to an open, and that we can Thevenize that circuit once the switch has changed state. Let's further suppose that in this box there are no inductors. The only inductor we have is right here. Let's further assume that we know its initial condition. I'll call that I of t0. But let's solve the differential equation for I of t. The rise in voltage is V Thevenin. The drop is going to be I times R Thevenin plus the voltage across the inductance, which is equal to L di dt. Let's pull the L out. So I just got di dt. Pull out an L from this term. Doesn't have one, so we'll divide by L. So we multiply this out, we'll get R Thevenin times I of t. Let's divide this equation by L, V Thevenin over L, and I'll put this on the other side of the equation as a minus R Thevenin over L I of t, and I'm just left with the derivative of I of t. Let's further pull out a minus R Thevenin over L. Now for this term I have an L, so I'll pull the L out, but I don't have an R Thevenin, so I'll put an R Thevenin here. So when I multiply this out, the R Thevenins cancel and I get V Thevenin over L, and then a minus sign, so these two minus signs become a plus sign. Let's divide both sides of the equation by this. We got di dt, and then the reciprocal of this. Let's integrate both sides of the equation, dt, from t0 to t1. The dt's cancel. I have the integral of 1 over I of t minus V Thevenin over R Thevenin di of t. As we showed in our previous video, that this is the form of the integral of dx divided by x plus a constant. And that's the natural log of the denominator. Natural log of I of t minus V Thevenin over R Thevenin, evaluated from t0 to t1. This side of the equation, you can pull out the constant minus R Thevenin over L because these are not functions of time, and I get the integral of 1 dt. That's just equal to t, evaluated at the upper limit minus the lower limit. Do the same thing here. We'll plug in t1, we'll plug in t0. As we mentioned for capacitors, when you have a difference of two natural logs, you can express that as the log of their ratio. Log of this term divided by this term would be the log of their differences. Just bring this term over here. Let's get rid of the natural log. Raise this to the power of e. E raised to the natural log is just the argument itself. And I can say it's this term also over here. And so let's solve for I of t1. That's going to be equal to this term on the other side of the equation, and then cross multiplying this with this. Here's I of t0 minus V Thevenin over R Thevenin times e to the minus R Thevenin over L, t1 minus t2. Let's do a change of variable, replace t1 by t, putting in these two terms. And now this is our solution to this differential equation. As we did for the capacitor, we could just call this some constant a1, some constant b1, and then t minus t0. And then I'm going to take the reciprocal of this term and call it again tau, and it would be L over R Thevenin. A1 would be V Thevenin over R Thevenin, and V1 would be this term, which is I of t0 minus V Thevenin over R Thevenin, and our f of t would just be their I of t. What is this term here? Well, as t approaches infinity, we get e to the minus infinity, so that's going to be equal to 0. We just get a1. Let's go back and look at the circuit and see what happens when that occurs. We're saying that the current I of t is equal to V Thevenin divided by R Thevenin, which implies that this is a short circuit. But that's consistent. We have that V is equal to L di dt. If the current isn't changing, it's constant, it's a DC circuit, then the derivative is equal to 0. Since any other voltage and current in our circuit, before we had Thevenized it, is related to the current in the inductance by some scalar, we could then do the same thing we did for the capacitance. This could be then any voltage or any current in our circuit. There would just be some constant here, we'll call it A1 or A2, or whatever you want to call it, and B1 or B2, and so on. To summarize this again as an algorithm for a step response. In this case, we've got one inductance. We could have many independent sources, many resistances, and many controlled sources. But the one inductance has the only term with a derivative in it. This is the form of the solution of a first-order differential equation. But now our time constant is L over R Thevenin. And this is the resistance seen by the terminals of the inductor, setting all the independent sources equal to 0, and then analyzing the circuit if it has dependent sources or not, as we did previously. The term A is when this term drops out, and that's as t approaches infinity, or really just 5 time constants. This term will become very small, and you get the value of A. Just evaluating our circuit, where we replace the inductor by a short circuit as t approaches infinity. Then the term A plus B is at t equal t0, and we know that the current in an inductance cannot change instantaneously. So if we find the value of the current before the switch changes state, it's the same as after it changes state, just for a small smidgen in time. And we can use that then to solve for B. Let's do an example. Suppose they have a voltage source, a resistance, and an inductance, and a switch that changes state from an open to a short at t equals 0. Let's solve for the current in the inductance and the voltage across the inductance. We're going to use our algorithm that we had in the previous page. I'll express it again as 6 steps. The first step is to formulate the equations. Any voltage or any current in our circuit is of the form A plus B times e to the minus quantity t minus t0 divided by tau. Since t0 is 0, it's going to have e to the minus t over tau. Since I'm solving for two things, I'll call this A1 and B1 and A2 and B2. Step 2, we're going to find the pre-switching conditions. And that's the value of our voltage and current before the switch changes state. So the switch is open. It's going to close at t equals 0. So this is at the time, I'll call it 0 minus, just a smidgen before the switch changes state. Let's assume that this has been hooked up for a long time. And that means we can think of the inductor as a short circuit, and V is equal to L di dt. If in this circuit there is a DC current or no current, then the derivative is equal to 0. That gives us the value of the inductor voltage at t equals 0 minus as being 0 volts. What about the current that's flowing through the inductor? Well, there's an open circuit here, so there's no current flowing. That's my value of the inductor current at 0 minus. I'm going to use this for making sketches. I'm also going to use it for the fact that I know that this current in the inductance cannot jump instantaneously. When I find the initial conditions of the inductor, in the next step I can use that. So the switch changes state, it now becomes a short at t equals 0 plus, just a little bit after 0. And the current that was flowing in the inductor before that was 0, and it can't jump instantaneously, because if it does, you have to provide infinite voltage. And of course that's not possible. That's going to be equal then to A1 plus B1 times e to the 0. Solve for the voltage V sub L at t equals 0 plus. Now there's no current flowing through here, so there's a drop of 0 times 10k. So we're going to loop counterclockwise. So the rise in voltage is what I'm solving for, then equal the drops around the loop. Now this is a rise in voltage, and you could think of it as a drop in voltage of minus 0, plus 9. Voltage across inductor, just 9 volts. In other words, this voltage is the same as this one because this is 0. And it's going to be equal to A2 plus B2 times e to the 0. Now notice here the voltage across the inductance went from 0 to 9 volts instantaneously. And it can do that. It's just a current that can't jump instantaneously. Step 4 of the algorithm, we define final conditions. What is the value of I sub L and V sub L as t approaches infinity, or really 5 time constants? And this is after the switch has changed state. And now I have an inductance in a circuit for a long time. It begins to look like a short circuit. And because V is equal to L di dt. So what's the voltage across here? Well, just equal to 0. That's going to be equal to A2 plus B2 times e to the minus infinity, so just A2. Current that flows in here is going to be this node voltage minus this node voltage, so 9 minus 0 over 10k, or 900 microamps. And that's going to be equal to A1 plus B1 times e to the minus infinity, just A1. Step 5 is to find the resistance seen by the terminals of the inductance with all the independent sources set equal to 0. So it's the short circuit, the switch is closed, and now look back into the terminals of the inductance, and you see 10k. My inductance was 1 millihenry, and my resistance was 10k. So instead of saying ohms, we could say volts per amp, and for the inductance, instead of saying henries, that's volts seconds per amp. The volts cancel, the amps cancel, and we get the units again of seconds. L over R Thevenin, in this case, is 100 nanoseconds. 5 time constants would be 500 nanoseconds, and that again is infinity for this circuit. Clearly not for us. And the last step is to find the solution. We had that A1 plus B1 was 0. A1 was 900 microamps, so therefore B1 is minus 900 microamps. I of t is A1 plus B1 times e to the minus t over tau. We found that the current was 0 for t less than 0, but if you evaluate this equation at t equals 0, you get 900 micro minus 900 micro times 1. So it's 0 also. Current cannot jump instantaneously, and so we can show equality here. Not true for the voltage across the inductance. We found that A2 plus B2 was 9, that A2 was 0, B2 is equal to 9. So it's going to equal to A2, 0, plus 9 times e to the minus t over tau. And then when t was less than 0, we found that the voltage was 0. We're going to jump from 0 to 9 volts times e to the 0, which is 1, or just 9. And this is the step response of an RL circuit with an example.